Okay.
Yeah.
So I wanted to begin by explaining to the chemists here the difference between a regular material that we study in thermodynamics class, like water and CO2, and a quantum material. So a regular material like water has melting transitions or boiling transitions that we drive with temperature, right? And well, CO2 sublimes, it does many things, right? But all of these involve thermal fluctuations. And quantum materials are different because the driver has quantum fluctuations. So it could be magnetic field, pressure, strain, sometimes even light or composition. So quantum materials give access to different parts of phase space and different properties of materials that you can't access thermal. They have no thermal counterpart. So I'm interested in external stimuli, particularly magnetic field and temperature. And these were a couple of areas I developed after much thinking as a graduate student, because you have to be different from your advisor. And I had the unfortunate situation of having an advisor who seemed to be good at everything and everywhere. Okay, I mean, he's active in, oh, for goodness sakes, condensed matter physics, certainly in ITC. Active in the search for axions. Of course, he never found one yet, but never mind that. Dark matter, LIGO, and gravitational waves. So what the man doesn't do, right?
He found a couple of gravitational waves.
Yeah, he found a couple of those. Yay, team. So I really wanted to stay with spectroscopy of solids, but I wanted to pivot away from what the boss did. And I think that's really important as you go for a career in academics. You don't want to be just like your boss. All right, I'm going to tell you 4 stories about my time here at the University of Florida, kind of 4 vignettes. And, we'll just stop whenever you guys are tired. All right. Uh-oh. Okay. So actually, I'm going to tell you the winding story of my career. Okay, the good things, the bad things, the happy endings, the successes, the failures. Sometimes I think that when people do these talks, they don't spend enough time talking about the failures. And in fact, I fail all the time. I think I fail 5 times a day. But you know what they always say, if you're not failing, you're not trying things that are hard enough. Okay, so I'm going to show you a few failures straight off. And at least now, in hindsight, we can laugh about them. At the time, I was crying in the stairway, but never mind that. All right, so I always knew, even from when I was a kid, that I wanted to go into academics. I needed to find my tribe, some people like me, it's not so easy, right? And I thought of other jobs. I didn't want to work for the man, right? I didn't want to start a company. I didn't really know much about national labs. So I thought, okay, let's do something challenging. Let's go lead a research team, which turns out to be really like a small business in a way. But one of the first things that I faced, and probably the most troubling, so okay, there's monsters here. If I really drew this correctly, the big monster would have been more upfront. The first problem or challenge I faced was not really like what to do, how to transition, but the 2-body problem. Okay, so how many of you ladies have scientific boyfriends? Yeah, it happens, right? Because, well, how many of the guys have scientific girlfriends? Okay, so you can understand this too. So my husband went off to a postdoc at Pacific Northwest Labs. I went to Canada to learn to do high magnetic field spectroscopy. And we stayed apart for 5 years. It was kind of sad and expensive too. So I can answer questions about that, but that's kind of the monster in my trajectory. Everything else is really very positive. So let's not talk too much about monsters. I want to start by telling you about one of the projects I did as a grad student. This was my first one. And I did it with a visitor from Budapest and, of course, David Tanner. And the idea is that there was a structural phase transition in this quasi one-dimensional material. So nowadays we would call this a charge-ordered material, and we could follow order parameters and so on. And I was always trying to make the boss happy. But I can tell you, I'm very sure I didn't succeed because he had this drawer, left-hand drawer full of Tylenol, and I'm pretty sure it was all because of me. Okay, but I had this idea. I had a friend from Pacific Northwest Labs, and I borrowed some diamond anvil cells, and I thought to myself, oh, won't boss be so happy if I take this charge order material and I apply pressure and I make it metallic. Oh, and boss didn't even tell me to do this. Do it all by myself, right? Okay, so I started the experiments. Everything was going fine. All of the features were moving, doing stuff. And then I heard the world's most horrible sound. What do you think it was? It was snick. Like, so the diamonds were broken. I'm like, okay, now so that explains the crying in the hallway at Williamson. Because I had to go tell David Tanner that I broke the diamonds. And not only did I break the diamonds, I broke the borrowed diamonds. So they weren't even ours. Like, uh-oh. So, okay, I was there for a while, finally screwed up the courage to go break the good news, right? So I told him the story about how, I just wanted to make him happy. I was just trying to give him a surprise. He's like, get up. So, okay, I ran back to the lab. And of course, I had to tell my friend who I borrowed the diamonds from, right? Yeah. And he said, oh, don't worry about it. I have lots of them. I'm like, yes. Okay. So that was one thing that happened in grad school, but I never forgot my interest in trying some high pressure work, okay? Because pressure is a really interesting external stimuli, right? You squish something, and what happens? You're changing bond lengths, bond angles. You're changing lattice constants, C over A ratios in 2D materials. So it's a really powerful tuning parameter. So meanwhile, I have a program on multiferroics, and these are multifunctional materials that are quite interesting because they have more than one ferroic order parameter, right? So they have these hysteresis loops. And these four ferroic orders are, of course, ferroelectricity, ferroelasticity, ferromagnetism, and ferrotoroidicity. And one of the really exciting aspects of this is because of the coupling between different channels. You can operate on the spin channel with, say, electric field, or on the charge channel with magnetic field or stress or so on. And these materials have lots of complex phase diagrams. Okay, so we were working on a lot of different problems, like how to raise the ordering temperature, right? How to increase magnetoelectric coupling and make it big and strong. And also, one of the commonalities of these features is they all have domain walls that can move around. And they have really interesting mathematical relationships. So we were interested in studying those. Okay, but, that in the back of my mind, I never forgot diamond anvil cell work. And I thought, gosh, we really should try high pressure studies. They're really quite rare. This could be a very powerful tuning parameter, right? So the American Chemical Society has a kind of a seed fund that many physicists apply to, by the way, if they want to try something new. So you really should write that down, the ACSPRF fund. So it's a kind of seed fund. They give you $100,000 in a couple of years to try things out. So all I really needed was a guinea pig, right? A friend, here's the friend. And his background is studying metallic hydrogen. and earth and planetary sciences, so very high pressures. So he thinks what I do is kind of like a baby, but that's all right. So I had a guinea pig student, Ken, and easy peasy lemon squeezy, I was back in the high pressure business with diamonds all of my own. Okay, so fast forward. So I actually learned how to use this diamond cell, how to load it, how to get spectra, how to take the pressure. All right, this is really important because, David Tanner, not only was he so busy with ITC and like, is there a gap? Is there no gap? Oh my God, what are we going to do? Right? You remember those days? He also was unlucky enough to be the department chair. And he said yes to being department chair the day before ITC broke. So when I joined his lab, I told him pretty clearly, boss, I don't want to do ITC. And he said, why ever not? And I said, look at yourself. You are looking at data you're not sure is right, that you don't understand on samples that might or might not be good. How is this a good idea? Okay, so I had lots of free time because, the unwatched graduate student is a pot that boils all the time. All right, so fast forwarding, I managed to transition this kind of exploratory grant into solid DOE support. And I'll just show you some examples of some of the things we've discovered. This is a fun one about piezochromism, where you can take a sample that starts life green, it goes from green to yellow to bright red under pressure to black, and then you release pressure and it's back to normal. I mean, when the student was doing this, he's like, holy crap, my sample turned red, what to do? I'm like, keep going, right? All right, and that's just because the band gap is marching across the visible spectrum. All right, and all right, so these are some of the culprits on that project. As you might expect, chalcogenides are really soft and they're incredibly responsive to pressure. So one system I've been working on recently, so yes, I still have my own projects that I do with my own two hands. Okay, because what? Because paperwork is no fun, right? I mean, I could spend my whole day answering email, doing paperwork, and eating my lunch, but that's not why I signed up for this. So I actually have projects and working on intercalated chalcogenides. This one is my project. So the idea is that you intercalate metal ions into the layers, they become chiral. All right, so this very strong mode is the vibrational mode. It's a phonon, a collective mode, basically a drumming mode of ion centers inside the layer. All right, and you can see what happens to it with pressure. Look at that. You go past, say, 3 GPa, splits into 3, and so on. So you can map out phase diagrams by looking at local structure changes. And if you do that for this particular system, and this shows structural phase transitions, the magnetic transition. Turns out this phase is ferroelectric. So this particular material could be a metallic, ferroelectric, that's also an altermagnet, and it's chiral, this particular. So I don't want to tell a long science story, except to say that, so like, I actually have a pressure program now after such a difficult start, right? All right. So, I really want to thank Peter and Rod for teaching two very different classes. Peter taught solid state physics. I don't know if he still does. Yes? Has anyone taken his class? Oh, please.
Sounds good too next semester.
Oh, I took that one too, but remember I made you promise never ever to let a chemist take that one ever on Green's functions, right?
Yeah, it's different now, but yes.
Easier? Less math, more pictures?
No Green's functions.
No, what? No Green's
No,
functions?
that's a different course.
Oh, okay. Oh. So I had two very influential
How's that
classes from correlated electron guys, okay? So obviously Rod works on small molecules, Peter works on solids and superconductors with particular interest in you know, sort of the gaps and their symmetries and so on. So I was lucky enough to be a member of Peter's first class he ever taught here. It was actually very influential for me because he explained everything in a way that we could understand. Okay, not just me, the other 21 victims in the class too. But one thing, and I was saying this to you the other day, it was quite a remarkable class because out of those 21, something like 13 of us went into academics. So really a very remarkable class. And I mean, Peter's had, just with that one single class, you probably never imagined you'd have an influence like that, right?
I had no idea there were that many. Like,
Yeah. Well, let's go make the list. So anyway, what I really learned, I think, from Peter is not only did I understand some of the solid state basics, right? But I understood the value of bringing theory into an experiment. So back in the old days, I'll just tell you, like 1990 was the old days. The theory wasn't that good. Okay, they could barely calculate a helium atom. I mean, come on. All right, but now it's pretty exciting. You know, theory is getting predictive, isn't it? I mean, you can actually calculate things and believe it. Who would ever expect that, right? So while I was very interested in bringing theory and experiment together in the early days, there really didn't, I didn't have so much of a chance to do that until maybe 10 years ago. Okay, where things have really gotten good. All right. So anyway, thanks to Peter and his exceptional class. All right, now you can go because you heard your thing. All right. So years passed by. And also another kind of influential thing is that there was a seminar at UF. I think it was a condensed matter seminar. And the magnet lab was just getting started back in 1990, right? The PIs won the magnet lab away from MIT. Woohoo, go team, right? And Mark Mizell was really excited about this. So it's really fitting. He's leading the high B over T effort now, isn't it? Okay. But that made an impression on me too, because one of the things I did for my postdoc was to go actually learn how to do magneto-optics, how to use these magnetic fields. Again, because I was pretty sure that David Tanner wouldn't. Okay, he was already so busy with all these other things. I thought, oh, for sure, he wouldn't do that. Okay, so what I want to tell the story about scientifically and how this course impacted my science is related to the Superlattice project. Okay, and this is a project about atomically engineered materials with the goal of trying to find room temperature multiferroics. And the idea is that you took these two materials, this 1,2,4 lutetium ferrite and 1,3 lutetium ferrite, basically AB, 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 and stacked them together in different ways. Okay, so each component brings certain things to the mix. Doesn't really matter what. But what I want to point out is that when you grow these superlattice films, are any people here film growers? No? Okay. Well, there's a problem with these films. Okay, well, it's not a problem. It's a feature, right? A feature is that without really reliable theory, you can't untangle the fact that there are so many different ion centers from these different components. Okay? So the film growers were making these different compositions, right? They could make 2-to-1, 3-to-1, 7-to-1, 10-to-1 layers, right? But look how many different iron excitations there are. and how many different types. So if I'd really thought about this beforehand, I would have run away screaming because it's impossible to untangle. Okay, fine. So fast forward, we were able to have a look at a bunch of different superlattices. This is a 3-to-1 lutetium ferrite 113 to 124 superlattice, 7-to-1, 9-to-1, and this one is multiferroic at 281 Kelvin. So my friends at Cornell call that room temperature, but it's cold in Ithaca, right? So it's not room temperature, but anyway. And the point is, I'm not sure if you can see this, but there's this lutetium layer distortion here. Okay, so the interface properties are what's giving the system this enhanced magnetic interaction. So we measured magnetic circular dichroism. This is a type of optical spectroscopy. Turns out there's optical loops, and we could show that it's actually the spin of iron 2+ to 3+ excitation that becomes so important in these 9-to-1 samples. Okay, and we couldn't have done that unless theory was able to unravel all of the excitations for us. Another thing theory could do, okay, this looks like a mess, right? Is people were wondering about the charge ordering patterns in these films. Okay, and this is the 3-to-1 superlattice. Okay, they wondered whether there was this ferroelectric single domain or this self-doped nonpolar system. So we came up with the idea, you know what? We have the magnetic circular dichroism measurements. All they have to do is calculate MCD, okay, with this expression, the trace, well, it's basically the XY component of the optical conductivity. My optical conductivity is a tensor. And you can distinguish between this one and that one. All right, so again, theory helps us distinguish. All right, here's the winner. A non-polar charge order pattern is the winner, lower in energy. Okay, and that can't be done without really high-level theory, a proper theorist working on the situation. So that's Craig Fenney's contribution. Yeah, he's a MacArthur Genius Award winner. Pretty nice, right? Yeah, nice. Okay, so very quickly, on to my news story, the killer. Okay. So you probably know that in 1990, there was a killer on the loose in Gainesville, right? So the problem, well, besides that there were like all these dead girls, is that the killer was leaving no clues. I mean, there really wasn't hair or any kind of DNA samples that could be used, right? And apparently he was particularly attacking blonde girls. That's me. So I was a little bit worried, right? Because the killer likes blonde girls. I'm like, uh-oh, what to do? All right. So one thing I really learned as part of that episode, as sad a time and as worrying a time as it was in grad school, I learned the importance of sticking together, working together. So the way we solved this problem in my group is that we moved into the lab. Okay, so there were 3 girls in my group. We had all the women in the entire physics department in my group. All right, and we had something like 10 guys. And so we were well guarded. And besides, the killer wasn't coming to Williamson, was he? No, probably not. Why would the killer come to Williamson, right? So, working together, we solved the problem of what to do about the killer. And during this time, some members of our research group were really scared. Leela, for instance, my co-graduate student, she had her now husband come down from Pennsylvania, and he gave up his postdoc to come down and guard her, and he took a job here. So sacrifices were made. during this time for sure. My husband was just busy doing his thing. Okay. Yeah. All right. But you know, this idea of working together and being able to work with top theorists is something that I never forgot, right? Because you know, your friends protect you from those bad guys. So this is my DMREF team. We had NSF DMREF funding for 9 years. And this is, this is our group. Here's Sean O, Valerie Kiryukin, David Vanderbilt, Zhang Chang, Christian Hala, and Wida Wu. Okay. I really grew to love these guys because, you know, they're just so quirky and excellent scientists. And we did outstanding things together. Just really imaginative things that we couldn't have done in isolation. Okay, so without working together, without cooperating, we couldn't have made the strides that we did. And I'll just show you very quickly an example of this. So you guys know what non-reciprocity is? Anybody? Well, you know what an invisibility cloak is, right? Harry Potter invisibility cloak. Okay, that's non-reciprocity. All right, when the optical properties one way are different than the oppositely propagated will be. Okay, so of course there are formal definitions, but it's really a very weird light matter interaction. It happens in materials that have ultra low symmetry and strong spin orbit coupling. So you really need some good choices of materials and big crystals. Okay, turns out it manifests in nickel tellurium oxide. And there's some surprises with it that I just want to show you. But very briefly, let me explain about this invisibility cloak business. So if you have a sample, and the reason it's green is because the sample's green, okay? So you send in light in one direction, it has some absorption coefficient, whatever it is. All right, but if you measure the other way, turns out it's different. So you have to be a really confident spectroscopist to realize that. Right? Really, really confident. All right, so it's not the same. And it's not magic. It's actually a consequence of symmetry. Okay, so you can write down some expressions for why that is. So the susceptibility, magnetoelectric susceptibility has two terms. There's a polarization matrix element and a magnetization matrix element. Both have to be non-zero. Neither one has to be super big. But that's why looking for non-reciprocity in magnetoelectric materials is a good idea. All right, and so you can measure non-reciprocal directional dichroists by measuring light going one way or the other, or by symmetry, you can apply field up and field down. Okay, so like I said, you know, this is a project that I couldn't have done in isolation. We needed every member of the team, not only to grow crystals, to grow single domain crystals, to do the new theory. That's part of it, right? Okay. So very quickly, one thing we found is that this system is non-reciprocal in the telecom range. Whoa. All right. And this data is at 60 Tesla taken in Los Alamos, a megalab. This data is at 3 Tesla. Why am I showing you 60 Tesla? Because I can show off 3 Tesla, more like a device energy scale, right? But the point is that never before has there been any evidence for non-reciprocity in the visible range. Okay, and this is near infrared. This is telecom wavelength range. Okay, with O bands, E bands, C bands. So in fact, I have them listed here. The C band is the conventional erbium window for telecom applications, right? All right, so the telecom fibers that we use these days are just drawn quartz tubes with erbium sprinkled inside. They're very kind of stupid things, very rudimentary. right? But what if we could use quantum materials and add new functionality to this C band or the S band or the L band? Okay, so one way we decided to do that was to look at a series of erbium-containing materials, because we already know the erbium systems are perfect for telecom, right? Except these are going to be lower loss. All right, so this work was enabled by the growth of single polar domain crystals, okay, by Sun Chong's team. Here's E band, S band, C band, and some temperature studies of the near infrared excitations. All right. And okay, so there's non-reciprocity in high magnetic fields, right? And you can even see avoided crossings and so on. But remarkably, there's non-reciprocity even at low fields here. And remarkably, even up to room temperature. So this data is taken at room temperature. Okay, so this is a project that would have never gotten off the ground without single domain crystals and the theory to understand the results. Okay, so power of working together. It's really, really important. Okay, and I'm just going to skip that. All right, the last story, and then I'll be quiet, take your questions. I'm going to tell you about the hole. Do you guys know about the hole in Williamson Hall? Oh, all right. Well, in the old days, there was a crawl space underneath the ground floor in Williamson Hall. And it was so dirty. And it was not a tall crawl space, it was like this. So when you went in there, you had to get down and crawl like this. And that's where they kept the pumps. And so every 2 weeks, whoever was responsible had to bring the tools, bring the oil, crawl half a mile in the dark. And it was so dirty, no idea. And there were spikes hanging down from the top, okay? Crawling. And even Leela, my co-graduate student, when she was 8 months pregnant, had to do it because nobody would take her shift. Yeah, because it was like so disgusting. And if you forgot like some tool you needed because something came up with the pumps, you'd have to crawl all the way back and get the tool and crawl back. Yeah, right? Okay. So I've set the stage. There was a crawl space. Wow. So David decided, I think I would like a hole in the ground that we can drill to, just go directly to our pumps, right? Not have to crawl the length of the entire hallway, half a mile, to get to these stupid things. All right, so he put in the request to maintenance. They came, they looked at the situation, they took a hammer. They're like, no. And they went away. Too much work. So weeks passed. Then David rented a jackhammer. And we had a Saturday group meeting. So I learned how to use the jackhammer. All right. And we drilled ourselves a hole. Okay. Turns out Yasu Takano was doing millikelvin measurements. That's it. And we introduced noise into his system. Okay, and he was so mad. Man, he was just like boiling mad, right? Boiling mad. All right, like our drilling, he couldn't figure out what it was. Oh, but guess what? 2 weeks later, he rented a jackhammer and drilled himself a hole. Okay, but he was mad for those 2 weeks. Okay, but the other thing we did, we might have drilled through a support beam of the building. So, a Williamson Hall support beam, it was in the way, right? Because where we wanted the hole, and because it couldn't be like where we would walk, because we'd walk right into the hole. So it had to be in the corner. So anyway, we just drilled through the support beam of the building. It seemed like a good idea on that Saturday. So David got in trouble. He was in trouble for the hole, an unauthorized hole. He was in trouble for screwing up Takano's experiment, unauthorized vibrations, and he was in trouble for drilling through the split beam of the building. And you know what he said to me about that? I never forget it. He said, you know, it's easier to apologize than ask for. Oh, okay, so he's right. He apologizes. Williams Mahal hasn't fallen down in these 45 years. It's still standing. It didn't need that support beam, did it? And Takano recovered. He drilled his own darn hole 2 weeks later and made his students write the jackhammer. Okay, so I learned that sometimes you have to take a risk. You have to jump. You have to learn new skills, like even how to use a jackhammer. All right, and I don't want to talk too long because I know you have questions, but I want to give one example of kind of how that idea plays into my own work. Okay, so there's a new technique that was recently developed called near-field infrared spectroscopy. It uses a synchrotron, an FTIR, and an AFM tip to beat the diffraction limit of light. So it allows you to do real space imaging of vibration. All right. So, you know, we had no funding for it. I had no students for it. I really didn't know what I was doing. But you know what? Sometimes you have to jump, give it a try, and eventually students and funding will come. I don't necessarily need to show you that example, but you know, it's almost malpractice for a spectroscopist not to be in on the ground floor of radically new transformational spectroscopic techniques, right? So even though I didn't have any funding, even though we were kind of unprepared, we had some good scientific ideas, could go out to the advanced light source and give it a try. And I'll just say that it's a tip-based spectroscopy, so the spatial resolution is pretty incredible. It's nanometer scale. All right, and I won't talk too much except to say that we were imaging domain walls in that particular case, and we're able to image hybrid and proper ferroelectrics. Okay, so I hope I've kind of given you a flavor for how some of the things that happened in grad school really made a difference later in life, and how I somehow managed to turn failures even into later successes, perhaps not forgetting what I learned, but trying something different. So I'll be happy to take the questions.
So after grad school, you went to postdoc. I forget where. Canada.
In Canada, yeah, I wanted to learn to do magnetic field work, and it wasn't a very common thing in the States. But they were really doing that quite a lot in Canada. I thought, okay, let's do this. But that really resulted in a long separation with my husband. You know, it took quite a while to get back together. And where he went to do high performance computing, you know, it was good for him, right?
So, you know, when you talked about doing collaboration with theorists, did you feel kind of like out of your depth in some of those conversations? How do you?
I always say, okay, look, let's be honest. Theorists, they're very smart people, but they just want somebody to pay attention to their theory, don't they? It's like, oh, please love me. Somebody must pay attention to my little theory, right? Someone please notice me in my theory. Okay, so you can ask them, all right, so explain this. Can you calculate this? Can you calculate that? What would happen if this? Teach me that. Okay, so they actually don't mind teaching you stuff because they think they're in the driver's seat when they're not. Because I told them what to teach. know, theorists are some of my best friends. Okay, but they don't do experiments either. Right? I mean, they would just simply be lost. What kind of glue to use to put a sample on a stick? They would be lost, right? One of my theory collaborators, well, I guess you know what density functional theory is, right? Do you know David? Well, he's not on this slide. David Vanderbilt? Okay, he's one of the inventors of DFT. But you know, if you go to lunch and there's 4 chairs and 5 people, he doesn't know what to do. So everybody has their strengths. No, I don't think that the experimentalist is lost. I mean, we don't have to understand the theory, we have to ask questions, right? And not too many questions. You have to be really careful with the theorists, not to direct them all over the place, right? But like, what do you really want answered? Like I tell my students all the time, if you have one question you want answered, what is it? Have a backup. Yeah.
For your like groundbreaking spectroscopy, did you have to like build instruments?
Sometimes. Yeah. Sometimes, you know, we do have to build things or interface things. These days, students aren't as good at it as they were years and years ago. But you know, some students are very talented in that area, right? I have one now, but the other 9 I'm not. So.
Question. So throughout your career, obviously the evolution's occurring in terms of the field and how things are changing, how you adapt. I guess this is a future question, just ChatGPT, not just, but AI is becoming really relevant. I think it'll be in chemistry at some point. I love some different fields, but not saying it'll take over. That's not what I'm just asking how you think you might use AI if you want to, or how it'll help you.
Yeah. Okay, so first of all, personally, I would stay as far away from that as I can. I like to think with my mind, and I don't feel all right. I know how to conjugate verbs, where the punctuation goes. And besides, NSF has rules against AI assisted writing. So if it's AI assisted, don't throw your proposal in. All right, so I don't want to use it as a crutch, and I do not encourage my students to use it. Although I know that some of them do. They say to improve their grammar and pronunciation. You know, I have deep misgivings about it. I don't know about you guys, but maybe in the more technical side, I think some materials identification with AI. So how to accelerate non-reciprocity in the telecom range, how to get big effects, what ingredients are. But of course, you have to have data to feed the AI. And if there's not a lot of test cases, then there's not a lot for it to extrapolate. So it's hard to say how much AI will impact my work. You know, sometimes we talk about it with my collaborators, but I always go back to the idea that you should do what you're good at and not what you're not good at. And if your thing is not AI based, well, God bless you, don't use it, you know. It's okay. We don't all need to just do some simple extrapolations between points to get where we want to be. So that's just one take on it. Right? I mean, it's different if you're building block copolymers and you mix A plus B to get C, and oh, how long should block A be? How long should block B be? I mean, oh, for goodness sake, sure, that's perfect for an AI solution. Yeah.
Was it ever difficult to like transition from like grad student to postdoc or postdoc to professor? Like, how was that experience?
Yeah, I would say that at least in the old days, young lady professors were not that well liked somehow, even by the women graduate students. So sometimes the fiercest critics were the female graduate students. Yeah, but I mean, I didn't really a problem transitioning because, I had plenty of funding very quickly and didn't really care what anybody thinks, so. Right? But whatever.
So I had a scientific question
Yeah.
about the non-reciprocity. So I'm like familiar with how spin orbit coupling in organic materials contributes to like organic species acting as spin filters. So
Okay.
is that in the context of reality similar to the non-reciprocity concept?
Okay, so what it does there is it blocks certain pathways because certain pathways require spin flip, right? And so it blocks certain pathways. In this case, it activates certain matrix cells and it breaks certain symmetries, time reversals and potential. Yeah, oh, that's a good question.
Very interesting. I love the scientific aspect you've got.
Oh, thank you. Thanks a lot. Yeah, I tried for variety here because I wasn't sure what my audience would be. Yeah. Any other questions?
Did you have any interest of going into national labs at any point?
Oh, sure.
Yeah.
I mean, I also thought about industry,
Yeah.
back in 1990, internet was new.
Mm.
I said to my parents, God, somebody really should start selling books and music and stuff on the web. And my mom said, why don't you start a company? I said, oh, for God's sakes, that is so trivial. I just got a PhD. Why would I want to do such a trivial, stupid thing as that? That was 2 years before Jeff Bezos. 2 years. And can you imagine? So I was too good for that. Or, I mean, but it's boring, right? And the poor guy is trapped on his giant ship. He can't even get off his ship without being a security risk, right? Yeah.
I have one final question for me. So you said, so 2 parts, you were already married before you guys did the long distance?
That's full, yes.
And then so during the long distance.
Yes.
So congrats for like doing that, that's like really honorable. But secondly, he's also science, right?
Yes.
Did
Yes.
you choose academia or industry?
Oh, so David always wanted academics. He did his PhD with Rod Bartlett. And correlated electron theory, and then he did parallel computing. At Pacific Northwest Labs with Robert Harrison and but he always liked the computational side. And in the end, he changed fields. He moved to Oak Ridge National Lab. He leads a computer science team there now. Okay, I moved to Tennessee to be with him. And I really gave up a lot to do that. Too much, but he's very cute. So I went. It's a situation I'm not proud of, okay? So I can tell you what I gave up. It's maybe interesting. So in New York, I was promoted and I had tenure. Okay. I became an assistant professor again. I lost my tenure, went to 30% pay cut. Okay. And they gave it up to solve the 2-body problem. Because in those days, it wasn't so easy to solve the 2-body problem. I had to beg them to hire me anyway, even as an assistant professor, but Laura NSF grants the DOE fund, right? Like more than anyone else in the department, but they had to check, make sure I was up to it. Okay, good, fine. I think in the end, it worked out. I'm still married, and I wouldn't recommend the separation. In fact, it's easier now because phone is so cheap and then so many technologies, much easier now. But in those days, we only saw each other every 4 months. There wasn't a lot. So that was really a very challenging time for me. And a time that it's like nobody else could really, people didn't appreciate. It's kind of hard to explain, but none of the guys would even appreciate how this could possibly happen. Right? Because if you have your wife at home and right. But I would say that many academic women have done this, at least people who are my age. Nowadays, that's not a choice that most young ladies have to make. but it was a choice in those schools. So. Yeah, but that's a long story with some drink associated. I should show you a picture of my research group. Yeah, they're so cute. Anyway, what were you gonna say?
We kind of talked about this before the talk, but or I overheard it, that you were maybe, I guess, about faculty searches and
Oh,
I guess
Hmm.
do you, I guess, how are you involved in any in the University of Tennessee? And like what do you, I guess, look for in candidates and what do you recommend?
you know, the one reason we have a committee is because people look for different things.
Right.
Right? And what I think makes a successful faculty member might be different from what someone else thinks might be successful. Right? Some people think a good assistant professor is a quiet assistant professor. I do not think that. Okay. I think a good assistant professor is a very busy, can do sort of person. You know, if you're told no, you have to find a new way. You don't just like say, okay, bye, walk off. No. Someone says you can't do this thing, you're like, by God, I can. And then you drill a hole, right? So I look, especially in these difficult times, these difficult funding times, I mean, I look for somebody who's resilient, someone who can make lemonade out of lemons, somebody who can take a disappointment and make it work. Because if you think you're going to hit gold on your first strike, I mean, you're nuts. So you need to have some real resilience behind you. And that means, unfortunately, failing a few times and getting a few knocks on the head, right? So I mean, I look for somebody with lots of energy because it's not a low energy occupation. Right? You really have to have lots of energy to have busy days and do experiments. And I think you have to have a lot of perseverance and the ability to handle setbacks. And you know, successes too, but don't want to be so into yourself that you know you think you're some amazing thing just because you're one success, right? Yeah, anybody interested in academics as a career? Yeah. Okay. All right, a couple. Good. Well, you know, and times change. I mean, sometimes people, you know, it's like something happens and their whole outlook can change on that question, right? So, yeah, I mean, what do your advisors say about academics? Anything at all?
Papers
Yeah.
matter.
Sure, they do matter, right? Productivity matters, of course.